Very good. Just to make a last comment of energy and sustainable energy use. In general, in particular in Chile, most of the companies are using renewable. For example, Sierra Gorda is 100% renewable, and it can come from this type of energy. Any idea what is this? And now this is a course of design. You are happy to join, but you don't need to stay. But if you want to stay, you can stay. Any idea what is this this plant? Actually, this is in Antofagasta. Cobra, what is this? Any idea what it looks like?
A solar panel?
No, they are not solar panels. Similar. Jamila, too? Any idea? You can speculate. You know, this is a game. It's not solar panel.
Photovoltaic cells.
Photovoltaic cells is the same as solar panels. It's the same, but it's not. They are not. Rudolf?
I was going to say the same thing. It's like a power plant or something.
It is, but not photovoltaic, not solar. Mugi?
No idea, Professor.
Again, don't be shy. I know you don't know. We will be visiting this plant. This plant, those are mirrors. Mirrors, the same mirror that you use for comb, to comb or wash your teeth. A mirror, big mirrors. I don't know, 5 by 6 meters. You have 1,000. I'm not sure if it's 1,000. This is a, listen up, solar concentration. And all the energy, solar energy, goes to this eye that you have here, black spot, all of them, listen, to have molten salts, potassium nitrate, sodium nitrate, 350 degrees. And you have liquid molten salt that goes to a heat exchanger to generate steam, and then you generate power. This is located in Chile, also in California. It's gigantic project. In my opinion, it's not a good idea because you have issue with materials. Okay, this is new for you. Did you know about solar concentration?
No, we don't know.
You can look, not now, you can look afternoon, solar concentrator in Atacama Desert, and we will visit that. It's gigantic. This tower is very, very big. It's even bigger than the Costanera Center, which is the highest building in Latin America. Okay. Because yes, Nana.
Yep. So they are concentrating the sun rays towards that let me see, black.
There, black spot.
Building.
Yes. Yep. No, this very tiny black spot, like rays, all the solar rays, solar thermal energy. And they will remain a huge amount of liquid molten salt, liquid hot molten salt, 350 degrees, and they have this big storage tank in order to keep during day and night. You accumulate energy during day to be used during day and night. That's the difference from solar panel of aeolic energy. This is more stable because you accumulate thermal energy in big tanks, big storage tanks, and then this thermal energy, it has a big tank. You see this big tank is about, I don't even remember, 500 cubic meters. It's big. It used to generate steam. It has a heat exchanger, generates steam, and then it goes to a turbine to generate continuously. It's a continuous energy harvesting because you have accumulated using solar energy, and we know that the solar energy is not always stable. Understand the concept, Nana?
Yes.
Okay. So I'm just putting this example because the main problem of renewable energy is stability. So you can solve that having a buffer. Okay. Ignacio, did you join us? Ignacio, we can hear you. I think it's not connected. I think I saw it, but I want to be sure that. Anyway, so the next picture, by the way, those is the first course students. What do we have here? We already know. We have photovoltaics, again, very large, gigawatts, and also aeolic plants. What is the main problem that we are facing here when we have this type of renewable energies? I already mentioned some. Rudolf, what is the problem that we have here? Rudolf, did you solve the mic problem? Your mic problem? Okay, I think you didn't solve it.
Contamination?
Yes, but no yet, because I mean, recycling solar panel is a big issue. It has not been solved. Recycling these blades from turbine also is just being addressed now. But yes, we will have a problem with solar panel. At the moment, they are being reused because they have less efficiency. But yes, there are already projects recycling, not in Chile, in Europe, solar panel. But yes, it's a very nice market for innovation on that. Okay. The main problem here is another one. I mean, I'm talking about an operational problem. Any idea of this operational problem?
So if I'm thinking, because the place is arid, it's dusty. If the wind blows, it carries dust to cover these panel surfaces.
Very good. Yes, it is indeed. It is indeed a problem. It's called Chusca because it has not been tested in this environment. Yes, it is a problem. The dust covers the panels. There are some specific material, another area of research, to avoid developing in Santa Maria University, a coating system to avoid the dust being deposited. This Chusca is a clay base, so it's very fine particles, so difficult to manage. Nothing happened with the turbine. An additional problem in Chile, the UV radiation is so high that we don't really know the life expectancy of the solar panels. But I'm talking about a different problem. Renewable energy in general has a big problem. Chile has the potential in both wind energy and also solar energy to solve the problem of the entire planet. I'm not kidding. The Atacama Desert, if you put many solar panels, we will not have problem with energy anymore. But there is one restriction. What is the restriction? Yamilatu, you can speculate. What should be another restriction?
To transport the
Very
power
good,
to
very
okay.
good, very good. Transporting energy is a big issue. And in between, you can have buffers, accumulation. So all these projects do not consider, please listen, all these projects do not consider accumulation. They don't consider accumulation. So the big issue is how to distribute the power generated, which is variable depending on solar panels, photovoltaic. It's a big issue. We will be visiting a center in Santa Maria University. It's called AC3, where they have an electrical system to regulate that. So in general, we have a very stable energy system, especially in mining. But all the time, we also have fuel-based power. I mean methane. But yes, transportation, we cannot convert this energy using cables, either alternate current and also a continuous current. There is a project in Chile for if you have more than 1,000 kilometers, you can use continuous transmission without losing energy. It's efficient. Above 1,000 kilometers. There are projects in China, in Russia with that, and was approved in Chile a transmission line with high power. It's not really continuous as the one that you use for batteries. it's a frequency converted in square waves, but the technology exists and it has been approved to be used in Chile. But yes, the carrying energy is a big problem. Any alternative to carry energy, Ignacio? Any alternative idea to carry energy? Because we cannot accumulate. This is far too expensive. Having batteries is far too expensive. Any idea to carry energy, Ignacio? I think it's not connected. Nana, any idea to transmit energy?
Power lines, batteries.
No, again, batteries is far too expensive. We do not accumulate, we do not have buffers. All this project, no buffers. Apart from electrical power lines, what alternative you have? If I want to send energy to Germany or China or Australia or US, Cristobal? Crystal? Any of you, please raise your hand. Yes. I'm sorry?
I thought it's Cristobal, sorry. No idea.
No, I said Cristobal, but he didn't answer, so then I moved to Crystal. Okay, guys, we have a seminar on that. I did a lecture, a web. Perhaps you didn't were connected, or perhaps you didn't. The way to transport electrical energy is through chemical carriers. Chemical carriers. You use this electricity. When you overgenerate electricity, you produce hydrogen, and you can carry hydrogen, which is not that simple. So what are we doing with hydrogen? Is being converted into ammonia, NH3, ammonia, and that is the idea, to chemically storage energy. If it's hydrogen, you can keep it for weeks. If you convert it to ammonia, you can keep it for months, and then it can be transported by ship. That is the idea. So that we call it energy vectors. Energy vector is the concept that we are talking about here, and more specifically, energy chemical vectors. Okay, Mugi, is that understood?
Is it by pipeline you're talking about for the transportation, or it's like how transportation is how?
We don't really know yet, because transporting hydrogen in pipes has restrictions because it's diffused to the metal matrix, and then it can create something that is, from material science, it's called embrittlement. It generates little corrosion. Okay? It's very reactive. There is experience of hydrogen in a petrochemical, but there is a concern from community transporting hydrogen. Okay, so the alternative is converting this hydrogen, once generated, into ammonia through a process called Haber-Bosch. I think we will come back to that, Haber-Bosch, which is developed in more than 100 years ago. And then you can transport ammonia mainly by ship, by trucks, okay, because it's liquid and it has less pressure. Okay, so the concept that I'm facing here is the unstable generation requires to have an alternative way to transport it. Okay, another comment on that: we have companies that are 100% renewable, but renewable energy, as you can see from this picture, is connected to the same matrix. So you have electricity coming from thermal plant, coal, methane, photovoltaic, molten salt with solar concentrator, eolic. But still, Sierra Gorda says we are using 100% renewable. How come? Honestly, it's very difficult because an electron, you cannot tell the electron where it's coming from. So everything is interconnected regardless the source of energy. Cobra, do you understand the concept?
Yes, I'm following.
Yeah, okay. So the company has an actual contract for a specific rate saying we are renewable, but not necessarily they are receiving electrons from 100% renewable. The installed power that there is in the Antofagasta region, in some specific days and time during the day, it can be 100% renewable. I mean, the city, there are some, not 100, I'm sorry, it's 93, 95%. So there are some specific spot. So we are close to be renewable, but never will be 100% because the generation and the harvesting of the energy varies. It's not stable, okay? And at the moment, there is not buffers, no batteries. Batteries will be very expensive, not chemical carriers. Okay, that's the current situation. So when you say that is 100% renewable, it's not all the time true. Okay, so I'm gonna close this point here. If there is any other question or comment. So we're reviewing 3 ways to generate: solar concentrator and molten salts, aeolic, photovoltaic. We have concern on the materials and the environment condition, dust and UV. And then we talk about the buffer necessary to distribute energy. The other concept was the grid, the interconnection grid, which is distributing different for different uses and sources of generation. Okay. Any question regarding this topic here? Don't be shy. Yes? Hernan, you have a question?
No, I have no questions.
Okay, now we will move to another topic. We use, I mean, a sustainable process design is not because it sounds nice, the name is in the fashion, it's because it's necessary to comply environmental regulation. So there are many standards, especially in mining operations. Remember that these acronyms stand for health, safety, not in terms of process safety that we use in chemical engineering, safety more with the operation, environment, community, and quality. Okay. So arsenic is a big issue. So if you analyze, this is a methodology, it's a box-based, process-based. If you analyze where the arsenic is generated, in the case of sulfur mineral ores like copper sulfide, in this different step, there is not impact of arsenic except in the smelter, where you generate a slag, dust, and then in the electrolytic sludge, there is little arsenic, but a lot of lead. First question: when we say this dust, the pyrometallurgical dust, where it comes from? This pyrometallurgical dust, Jamilatu? Where is coming this metallurgical dust?
The dust from I think the comminution stage.
No, we talk about, listen up here, look. Different step, rock mine, okay? This is blasting, then crushing. Concentrator. In the concentrator, you have the comminution. You don't have arsenic there. I'm talking about the pyro process. You generate dust with arsenic. Why?
From the smelters?
Yes, it is in the smelter because it's pyro, but I'm talking about where.
I believe it goes to how can I say this? It's a plant that processes fumes, and it produces, for example, uh, 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 sulfuric acid and some other pure substances such as arsenic and such.
I'm talking about the dust. You are close, Ignacio, because I know you
Well,
were in a yes, you are close, but it's
I
not the
think
answer.
that's yeah, right. Those stream gases that coming out of the smelter that have some I don't know those salt particles that might be separated as
Yes,
we have
particles
with the copper
separated.
electrostatic separator or the boiling.
That's the
Yeah,
point.
so
That's the point. This dust is generated or separated in the electrostatic precipitator. Electrostatic precipitator. And these particles are really, really, really small. So all the piping must be really, really well sealed. But you also have fugitive gas that includes this dust. And if you go to a smelter, and it's very easy to see when you have dust. You just need a laser pointer. When you have a laser pointer, you will see, like when you put the laser pointer, you will see the air like smoke. This smoke is showing particles, very fine particles, and the width of the smoke, it's related with the particle size. This is use a phenomena called a light dispersion, the same that we use to determine particle size distribution in the low range. This is a laser scattering analyzer, okay? So the dust is generated in the electrostatic precipitator. Those are micro droplets that are being cooled down and collected as a very, very fine dust, the one that you are using now in your sustainable project. Okay, that's understood? So this dust,
sorry, just one question before
yes,
going forward. We also have after the smelting that these gases, this stream, going through the waste heat boiler, right? It is two separate process, the electrolysis precipitator and those boiling waste. I don't
it's more
know.
complex
It's
than
like
that. It's more complex than that. Hopefully we will visit in Caletones to see it. But in short, you take all the gases from the smelter, mainly you remove particles with the electrostatic precipitator, then it goes to a wet scrubber, and more importantly, you have SO2, okay, that goes to a catalytic reactor to generate SO3, and then this SO3 is absorbed in sulfuric acid to generate sulfuric acid. Believe it or not, smelter like Alto Norte that is owned by not Glencore. I don't remember. Anyway, in this company, the income of this company comes from the sulfuric acid generated, not for the processed copper. Believe it or not. So these smelter plants are really to generate sulfuric acid for, of course, leaching. Okay, so you have separate process. Energy, not really. Energy is not used to. It can be used for steam generation, but really no. Actually, the smelters are they generate their own energy. It's a combustion. It's a combustion of sulfur, and yes, very good comment, Cobra, because you generate a slag, a molten material that it's about 1,200. It has a lot of energy. Today is not being used. We apply for a patent. We can come back to that. Apply for a patent to recover this thermal energy and accumulate it in some point. But it was some similar idea in Germany, so we didn't succeed the application. But happy to come back with that because they have a lot of energy that is not being used at the moment because they are not interested. The plant, the main consumption of energy, as a fuel, it is in the drying process. When you have the concentrate, you dry the process with a fluidized bed or rotary dryers, and they consume, let's say, a truck per day, 20 cubic meter per day in a standard operation in the dryers. But no, energy is not generated. Okay, Cobra, did I answer your question?
Yes, but I remember when we were looking in those copper smelter, those stuff, some papers just doing some comparison between the dust coming from that boiler and this precipitator and show that okay, that boiler dust have a better treatment and that the oxidized is and the particle size are different. Just in case
Then I
that the
don't.
treatment
I'm not following. What do you mean by
is better.
boiler? It. You mean you use the heat to produce steam? We're talking about that.
The energy point is another one, but regarding those dust coming out of this boiler.
But it doesn't come from the boiler. The dust comes from either the pyrometallurgical process or the combustion. Because in a boiler, you burn coal, you burn diesel, and you also generate particles. You're talking about that. This is a different thing.
Okay.
Let's say in a thermoelectrical plant that uses coal or even diesel fuels, they do generate a different particles, and this is called fly ash. Fly ash is the term for when you're talking about that. But in general, a smelter, actually they do have steam, but they don't recover the heat in general, which is a bad idea. Okay, is that more clear, Cobra?
Yeah, it's okay. Yeah, it's okay. I got it.
Okay, let's come back to
Sir,
this. Yes, go ahead.
sorry, I wanted to add something from my experience in the smeltery that I had my
Good.
internship. Uh, the residual the waste heat that they use in the furnaces is often used when they also have a electrolytic electrorefinery stage. Uh, they often use the residual heat to heat up the electrolyte.
Okay, thank you for introducing the concept. Residual heat, if it's really, really hot, it can be used to generate steam. But in some cases, when the residual heat it's low, we're talking about 150, 200 degrees, it been used in something that we call ORC, that is stand from organic Rankine cycle. This is for residual heat. That means you can have a turbine that uses less enthalpy, less energy, and they use, for example, butanol as a liquid that is being generate steam, butanol, and then go to a turbine. This is an interesting case that I just learned from this conference in Finland, in Helsinki. All the all the domestic waste goes to a degradation plant when they generate methane gas and also material that is being burned in a combustion chamber, and they have a generator, and the residual gas is used for heating the city and also the organic cycle. They're coming back to ORC. ORC are not efficient, are 10-12%, ORC 12-10%. We will see ORC cycles as a case study for geothermal energy. This is called medium enthalpy geothermal energy. Okay, so I'm trying to explain you can still recover heat of low enthalpy, talking about 100, 150 degrees. Okay, Ignacio, did you understood that? Are we clear with that?
Yes. Thank
Very
you.
good. Let's come back to the flue dust. My interest now is arsenic from flue dust. So you were able to collect the dust. Most of in this case, they have arsenic trioxide, which is extremely toxic. It's difficult to treat. So this company is Codelco Ecometales. Codelco Ecometales has developed a technology of leaching, but this leaching process, since it's a very, very small particle size, works in 10% solid content, which is not a standard. It's not a standard design for leaching pulps or leaching particles in agitated tank. The standard should be 30–40%. Otherwise, the equipment is too expensive. But they did it in Codelco not because the process was designed like that. It was done by that because these reactors, which are 1,000 cubic meters, were available because there was an original project between BHP and Codelco. It was a joint venture project for bioleaching. So this gigantic reactor, because it requires a large residence time, didn't work because the shear stress, the mixing killed all the bacteria. So they have, as an investment project, they already have the equipment and they use it. Okay, because if you want to do it as a project from zero, from scratch, the economical evaluation will not be beneficial. So that's the case. In short, they have many steps. It's a batch, semi-batch reactor with a very low concentration. It's a tip for the next presentation, very low concentration. They use sulfuric acid and also the oxidizing agent. Remember, we talk about Purvé diagrams. Remember, we talk about Purvé diagrams or a PPH and a speciation. We will come back to that too in the leaching topic. They use as an oxidant peroxide, which is H2O2 peroxide, which is really bad idea because you need to transport that by truck, and is by regulation cannot be that concentrated. Okay, so in short, this is the process. You have precipitation, and the good thing here, you have the right condition to generate scorodite. The scorodite is the most stable, as I mentioned before, the most stable component that passes the heap leaching test. It's the only plant in the world that processes, huge amount of material. It's the largest. There is another one in Japan, similar to this, that it processes only 10% of this. This is the largest plant in the world. We will visit it. This is the detailed process. This is the product, the scorodite product, and you're removing 3,500 tons of arsenic. Okay, so we'll be visiting this plant. We don't need to go into detail. This is the peroxide. This 70% peroxide is really uncommon. You cannot have as a reagent this 70% because the regulations, I want to insist on that, the transport regulation restrict you to use as a chemical reagent peroxide with no more than 50% or 40%. I don't really remember. So the current regulations in Chile are for less concentration because it's a very powerful oxidant. Okay, what happened here? It's not possible to use 40% or the regulation number because you are transporting water. It's too expensive. So this company is a Chilean company. They changed the regulation specifically for Codelco in order to transport 70% peroxide. Why I'm telling you this? Because when you are designing a process, and when you define the reagent that you're going to need, you need to know what are the concentration of the product that are acceptable for transportation. Okay, is clear at this point? Mugi, do you understand the point? Can you summarize the point that I'm just describing? Summarize what I'll just tell.
Yeah, in my understanding, you explained that the arsenic is hazardous. It needs to be stabilized. So the company using here is peroxide, but exceeding the limit in the regulation. But specifically for this procedure, because it's arsenic stabilization, the regulation is modified to produce scorodite here.
And the learning from this experience is anytime that I'm designing a process, I need to consider the regulations regarding the concentration of my reagents. Imagine that you are not allowed. You design the process with 70% and blah, 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 and then you propose the project and send a regulation. You cannot transport peroxide. You need to add a concentration stage. That is the message, Mugi, okay? But you did a very good summarize, okay? Good? Everybody understood?
I have a
Crystal?
question. This
Yes.
is the present flow sheet that they're following now in the Codelco, right?
I can be
They're
certain.
converting arsenite to the Codelite? Scorodite
No,
now?
they are doing it now. They are changing the process. Actually, they are moving from this oxidizing agent. They have a new one, but we will be visiting them. So you will know more in detail of the process. You will see the equipments, okay? They're changing that. Following this oxidizing agent, please write down, for me, the best oxidizing agent, both generation and concentration control will be, what I have in mind, what will be the best oxidizing agent?
Ozone.
Ozone, O3, yes. Because it's generated on site, it requires only dry air or oxygen, but it's not as expensive as you expect, and you will be working with ozone reactor here to oxidize methylene blue to see how it works. But ozone is my recommendation for whatever oxidizing process. In fact, it's being used for water disinfection. Okay, so it's something well known from application in I mean the EPA standard in 1996 was using ozone. Okay, let's move forward. So this is the Ecometales plant. Those are the 1,000 cubic meter reactor. They are really big. And look our clothing. This is our clothing because it is a very toxic plant. With even there when you dump the dust, you cannot avoid fugitive gas with these particles. So we use this disposable suit because we're working with arsenic. Okay, so don't be afraid of that. Okay, so then describe a little bit the process. Oxidation, then iron sulfate in this proportion. Those are the part of the reaction. They control the pH, and in order to precipitate scorodite. Okay, that's the chemical reactions. And this is the comparison table for a different author here. When you talk about this TCLP test, this is a toxicity characterization listing procedure. This is a standard method from EPA 1311. This is something that you should know if you want to see if your product is stable, environmentally stable. And now you compare different alternative molecules. Calcium arsenate, for example. Calcium arsenate, it contains 12% arsenic, so it's not that concentrated. It means you have more volume. If you compare with crystalline scorodite, so that means you have double volume. And let me see. Okay, let's see here. When you apply the leaching test to determine if it's stable or not, the remaining solution, it contains 0.2 milligram per liter of arsenic. All other alternative, look this one, arsenate, 430. Compare with that. Why I'm taking in consideration this? Because this is the actual process in smelter. If you see smelter, it's calcium arsenate, which is not stable. What is doing Radomir Atomic? What is doing Chucky? Is doing calcium arsenate. So you can compare. Well, Isidora is here, but it's not part of the course. But anyway, Jiru, did you understand this comparison table? Can you summarize this table with your understanding?
Sorry, I went to the toilet. So
Okay, you can take your cell phone. No, just kidding. Nana, your summary. Nana, your summary.
Yeah. So can you hear me, Prof?
Yes.
Yep. So with the understanding I got from this was you started by saying whenever you want to do a leaching test, you need to compare it with the EPA method 1311, and then from this table we could see that with the stabilization of arsenic, you need to compare it with the arsenic content at the end of the reaction, and then also the solubility by the leaching test. After that, what the residue of arsenic that you get. So you compared it with the crystalline scorodite, and then it was 0.2 milligram per liter, that's ppm. And then you said that the traditional method that is being used in the smelter plants is the calcium arsenate, and then its concentration was very high.
Close. Because I didn't explain, I didn't explain properly. That's the reason, because I asked you to, what did you understand? Okay, this table compares different alternatives that are currently used to stabilize arsenic. Okay, so how can we tell which one is best? Okay. So the common alternative is calcium arsenate. This is the most used. And crystalline scorodite is the one that we just presented in Ecometales, the largest plant in the world. Okay. And how do we know which one is the best? The easy thing is to see the content of arsenic. For example, calcium arsenate has 12% in solid, scorodite 28. That means you have more concentrated scorodite in this molecule, in this mineral, in this crystalline form. One thing. The other thing is you need to apply a standard test to determine if the residual crystal, the residual dust, the residual sludge will be stable for a long time once you deposit. You see, once you deposit your here, once you deposit landfill. In landfill, once you deposit your, in this case, scorodite with water, you need to demonstrate that it's stable. What it means is stable. If it rains, if it has water, arsenic will not be dissolved. So to do that, we apply this TCLP test, which is toxicity characterization leaching procedure, and there is a specific standard for that. And then we compare the residual solution, and we're saying here, for example, after applying the test, we have 0.2 milligram per liter in case of scorodite. All other technologies are not that good, but more importantly, this is really, really bad. But this is very cheap because you use a calcium sulfate. Okay, so that is demonstrated in this table, a comparison of the different process design to stabilize the arsenic. Okay. Now we will move. What about the time? I think Yeah, I think we need to stop. It's gonna be 10. Okay, sorry, I've lost the 10:42 because we start at the, yeah, because we start at 11:05 local Chilean time, the presentation of sustainable engineering. Okay, so I ask you again to review the 4 documents. Please study before. If you need a printed version, you can go to my office, Mugi, and print it. But I want you to be familiar with the next topics because they are, for most of you, they are new. We're talking about mass transfer, kinetic, scaling up, interfacial area. So I want you to be familiar with the terms in order to facilitate the assimilation process. Okay, so we'll stop here unless you have an additional comment.
Hello?
For a moment. Can you hear me now?
Yes.
Yeah, I was asking Cobra a short summary of the thing that we are doing or presenting in the context of design. What are you
Should I
taking
answer
from
now?
this discussion? Cobra, go ahead. Yes.
Okay. The overall discussion about this, actually, it started from those turbine. No. It started from
Yes.
those
Energy,
basically,
yes. Energy,
yeah,
renewable
it
energy,
started
yes.
from this energy, and the next the challenges that we have in the turbine regarding this flow and the transportation that we have in this renewable energy, that we couldn't say it is
Very good.
100 in neither of the cases. The best location is put in 90 or 95. Then the next one, if you go
Transport as a energy vector.
Yeah. The transport was a
Energy
challenge
vector.
here, and
Yeah.
it's going to be through the chemical or the other way, but
Yes.
not implemented yet. And here the challenging that we have in the process and gas treatment as a sludge and dust. We should do something here, and the Codelco as a present project that they're doing. And in the previous, they just stabilize it as a calcium type, calcium compounds of the arsenide, but presently scorodite show a better alternative for, and the oxidine that you mentioned, which is 70% high concentrate. So the best alternative will be ozone.
And the comment was, when you have a design, you need to consider the concentration of your reagents and regulations.
Yeah.
Okay. It's the process.
Oh yeah, it is
and
the
this is
process.
important to understand.
But the process, what I didn't catch is that you previous time, I remember the
How
first
do you
time that you
determine it? Yes.
the first time that you're talking about this BHP and the Scorodite, you told us that they stabilize it in the form of the calcium, right? But they
No,
presently
no, no,
changed the
no,
plan.
no, 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 no. I'm saying if you have this process design, since you have 10%, you need huge reactors. So
Yeah,
the
yeah.
process will
And
not be
still they have
economic.
Mhm,
They have a previous project based on
mhm.
bioleaching with bacteria.
And
It
it
was a
was
big
not related to
consortium.
the arsenic, right?
No, 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 no. It was not the
Okay.
arsenic. This is related with bioleaching, not related with
Mhm.
arsenic.
They
For
already
bioleaching
had
of
it before. Okay.
yes. So yes, that is a successful plan because they already have the equipments. It was a to leach
Sorry. Okay.
sulfur with bacteria. This match the economic.
Professor, we couldn't hear you because we're missing some parts of your audio.
I'm so sorry. I'm telling that this is
Okay.
an interesting case because if you have a process designed for that and make the economical evaluation, it will not pass because tanks are too expensive since the particle size is too small. So that was
Mhm.
they have the tank for a previous project that also failed. It was bacterial leaching for sulfur concentrate. Since they have the equipment, they can go to the project. That's the reason they can have the largest plant in the world treating arsenic. And the
Yeah, I
last
know, but
idea,
for
the last
Mhm.
science, yes,
Oh, okay, just one
I'm
small question.
listening.
In this case, in the case of Codelco, okay, because they have this investment, so they use those tank. But in the case of the other project or other factory, what
Yes,
they doing with it, with this mixing of those fine particle, what is the present or the technology that they are doing with this mixing the fine?
it will be too expensive.
Okay.
It will be too expensive having this large tank, and if you make the economical evaluation, it will be negative. Okay, this is $10
But
million
now the that
investment
but
already.
they going through it because they don't have any other choice. The other company or
No, no. I mean, I'm expecting from this group invent a new process, actually have some ideas.
okay. Mhm. Okay.
And Prof, I have a question.
I couldn't hear Professor.
Hello.
Okay, can you hear me?
Yes, Professor.
I'm sorry for the delay. I have a call from Santa Maria. I need to solve a problem. So we can start with the presentation. There is any specific order? I suggest that who's presenting should have the best, sorry, no, my camera, should have the best internet connection, preferentially from Santa Maria University. So let's start with Eduarda. Who in your group, Eduarda, can present?
Okay.
Do you have the presentation, Eduarda? Who has it in your group?
I think Sarah has it.